Hello, everyone, and welcome to our video presentation of our deep learning data science final assignment. Our team is composed of 5 members. We have Li Chaodonghui, Hyungjin Yi, Emile Albach, Manuel H, and myself, Keina Seban. The subjects we decided to tackle for this assignment is a study comparison of the pre-trained VIT model and the zero-shot learning model on the specific task of breast cancer detection. Indeed, breast cancer, according to the World Health Organization, was reported diagnosed more than 2.3 million times in the year 2020 and caused the death of almost 700,000 people. Nonetheless, early detection and early treatment reduces massively the cancer fatality, and this is done through regular mammography screening. However, the accuracy of these screenings rely heavily on the expertise of radiologists, a resource that can be very scarce in certain regions of the world. Moreover, one of the main issues that comes from these tests is that it often results in a high rate of false positive. In our comparison, we will be fine-tuning a vision transformer-based model using a tailored dataset in the quest of efficiency. This approach not only tackles issues related to data scarcity, image complexity, but also prioritizes computational efficiency, making it applicable to a real-world scenario, which is our case. And we wish for our work to contribute to a broader goal of reducing breast cancer mortality by enhancing early detection access.
As for our method, we leverage a pre-trained vision transformer model, or specifically VITL. We fine-tune the vision transformer model through a parameter-efficient technique called low-rank adaptation, or LoRa. We also apply domain-specific data augmentation techniques, including translation, sharing, and rotation, to improve the training performance. Now I'll talk in detail about the vision transformer model. This diagram here illustrates the vision transformer architecture. We first split the image into fixed-size patches and flatten the patches. We then feed the patch sequence and learnable positional encodings into the transformer encoder to obtain the image embedding. The low-rank adaptation technique, or LoRa, is a parameter-efficient fine-tuning technique. It is especially designed for fine-tuning of large language models. For fine-tuning with LoRa, we freeze the pre-trained weights W, and add a trainable rank decomposition matrix to each layer of the transformer architecture, as shown as A and B here. During inference, we merge the matrices with the original weights to avoid extra computation. Now let's move on to zero-shot learning with matclip. With a pre-trained matclip model, we can perform classification in a zero-shot manner. For the two types of labels, cancer and non-cancer, we first generate the corresponding prompts to the two types of labels. For example, one set of possible prompt is the healthy breast prompt for the cancer data, and likely breast cancer prompt for the non-cancer data. We feed these two types of prompts into the text encoder to obtain two text encodings, T1 and T2. We also feed our test image into an image encoder to obtain the image encoding I1. We then perform inner product between I1, the image encoding, and T1 and T2, the text embedding, to obtain the two inner products. The inner product with a greater value will decide the final prediction.
Our results. First, our experiment highlights the sensitivity of matclip's performance to the choice of different prompts. We can see there is a clear trade-off between the accuracy and also the recall in different configurations. And for fine-tuning VIT, we can see that overall performance of F1 score and accuracy are actually more balanced and more acceptable compared to matclip. And for our ablation study on the fine-tuning, first, we can see the full training method generally showed a tendency towards higher accuracy in predicting cancer, and also indicating that there is a potential bias in detecting the cancer cases. And for the LoRa adaptation, it shows that a more balanced performance between accuracy of cancer and non-cancer is achieved by the higher F1 score compared to the original one. And also data augmentation and loss function adjustments for example, using focal or using cross-entropy, actually significantly impact the model's performance, suggesting that these factors are critical in training robust models. So to conclude, our study showed the effectiveness and challenges of using advanced deep learning models, such as VIT and MATCLIP, in medical, especially in breast cancer detection. And the ablation study highlighted how important different configurations and the use of LoRa are for achieving an efficient adaptation. And also the varied performance of MATCLIP model under different prompts has stressed the importance of prompt selection when you are using the pre-trained models. So that's all for our presentation. Thank you.